Welcome further maths students to chapter 9. So far in recursion and financial modelling, we've been looking at some linear growth, linear decay, and geometric growth, geometric decay. And finally in chapter 8, we looked at effective rate. Moving into chapter 9 now, what you'll see is we start to combine linear and geometric growth together so that we can model something called a reducing balance loan, which is a little bit different to what we've been studying so far, a little bit more complex. But what we'll do is we'll break it up into a few little bits just to make it a little easier. To start off with, all we're going to do is look at combining the linear and the geometric growth together in a recurrence relation. So you'll see in this starting box just here that I have a starting value. Most of the time we'll call that a principal. And to get the next term in recurrence relations like this one, we're going to be looking at multiplying our value by a number, so by r, but then we're going to be adding or subtracting a value after that. Hence why we say it's combining linear and geometric growth, because you'll see that that part there, the r part just here, that's what we would have done when we were looking at geometric growth and decay. And then if you have a look at this bit here, this component is the linear component. So that's the geometric component, and this is the linear component. Now, we haven't done this before. We've, of course, had separate recurrence relations where we were exclusively looking at geometric or exclusively looking at linear. And so now we'll see what happens when we put them together. I mentioned before that we'll be looking at reducing balance loans. However, to start off with, we're just going to have a practice with using this recurrence relation. So it's not in a financial context yet. This one here is talking about land in a wildlife reserve that's put aside for an elephant habitat. So we've got here VN being representative of the area of that elephant habitat. That's going to be measured in square kilometres, and N here is in years. So the change in this habitat from year to year is modelled using this particular recurrence relation. You see here we've got V0, so that must be the initial or the starting area of the elephant habitat. And if you look ahead, you'll see that's what we're asked for in part A. This bit here, 0.85 times Vn, means that we're multiplying by less than 1. So it means that we're actually losing a bit of habitat to start off with. This here is our R value, and since it's 0.85, this represents a loss of 15%. The way I know that is I know that to get R, I do 1 minus the rate over 100. And so to get 0.85, which is my capital R value, if I wasn't sure, I could solve for R, but I can see I'm basically left with 85% of the habitat, so I must have lost 15% of that habitat. Then after that, you'll see we're adding 500. So whilst we lose 15% of the habitat, we're then having 500 square kilometres added after that happens. So if we have a look at these questions, what's the area of the elephant habitat initially? It must have been this value over here, which is our starting value. So we'll say 14,000 and we'll add in our unit square kilometres. This next question is asking us to describe what's happening year to year. So basically describe this part of the recurrence relation and then that part, the plus 500. So we established that it's decreasing, so it decreases by 15%. And after that, 500 square kilometres is added. Now, what we want to do as well is see, well, when you take off that 15% and then add 500 to it, is our new habitat, is it smaller or is it larger than before? And then when that happens again, is it smaller or larger? We should have a look at whether overall, are we losing habitat or are we gaining it? Now to do that, the easiest way is to get your calculator open and to set up this sequence on your calculator. So 14,000 goes into the calculator before we go 0.85 times by that answer plus 500. And if we have a look at the next one, 12,400 11,040. As we can see, over time, the habitat is decreasing. So overall, the area of the habitat. Just so that I've got a summary of what's happening year to year. I've got mathematically what's happening, but also overall, the area of the habitat is decreasing year to year. Now, in this final question here, it does say to write down a calculation to show this expected area of the habitat after 1 year. Now, I've done that on my calculator already. I saw that it was 12,400. There it is there, that second value, V1 in other words. But if I need to show a calculation, I'm really showing that I'm using this recurrence relation here with my initial value of 14,000. After 1 year, we call that V1. And to get V1, we take 0.85 and multiply it by the term before it. The term before it was V0, so that's 14,000. And then I add the 500. So just here, I've demonstrated what calculation brings us to this new area of 12,400 square kilometres. Finally, we've got after how many years does this area of the habitat first drop below 8,000 square kilometres? Now, since I don't need to show a calculation here, I can go back to my calculator. I might just count where I'm up to because as you can see with the one I entered to, which was 8,900, I haven't dropped below it just yet. So if we have a look here, 12,400, that was after 1 year, after 2, after 3, after 4, and I'll just press enter again. That's after 5 years. And so if we go for the 6th year, we can see it drops down to 7,356. So after 6 years, that's the first time it drops below the 8,000 square kilometres. Might just make a note, V6 was 7,356, ... So therefore, it's after 6 years. Oops. Here we go. So there's an example of using a recurrence relation where you've got both geometric and linear growth. Just before I finish with this part, we've got here combining linear geometric growth and decay, but this time looking at it in terms of an exam question. So what you'll see is this one's taken from the sample exam which the VCAA provided in 2016. And if we have a look here, we're asked about picking from this list a recurrence relation that's going to generate a sequence that shows geometric decay. So it's looking for values that decay geometrically. Now I wanted to touch on this one because when I say that these sorts of recurrence relations combine geometric and linear growth, they do use both of those elements of geometric and linear growth. When we actually generate the sequence, we can't say that the sequence shows linear growth or that the sequence shows geometric growth or decay because it actually doesn't fit into both of those categories. We're not going to find there be a common ratio, so it's not geometric, and we're not going to find there be a common difference either, so it's not going to be classified as linear. So I just wanted to mention that because often when we're saying combining the two, then there's sort of this idea that, well, it is linear and it also is geometric, but it's not when you create the sequence. I'll show you what I mean. First of all, let's eliminate ones that are clearly not true. So if we want geometric decay, we don't want to see anything here that's linear. And so if you have a look at that one, that's subtracting D, in other words, that is linear, so that's not geometric, so we'll take that one out. The one underneath it as well, this is adding a value, so adding D, that's linear as well, so not geometric. The next thing you might like to do, since we want decay, so we want to see our values going down or decreasing, eliminate anything that's being multiplied by a number greater than 1, because that takes us to a sequence where the values are increasing. So that's growth just there. That, of course, leaves us with two results. Now, if we have a look here, this one here, yes, is geometric because it's got just a number, left a T out there, just a number being multiplied by the term that comes before. So it's in this form, R times Vn. And also because R is less than 1, it's at 0.65, that is decay. So it ticks both boxes, and so that is our answer. I wanted to mention though, why is this one not geometric decay? This part looks promising because it does have R less than 1. The issue is this bit here. Now alone, that bit would be geometric, and on its own, subtracting 100 like we saw up there, alone that is linear. But when we put these together, so I'll just show you, when we create a sequence using that recurrence relation, you'll notice that our values are, I'll just maybe do the first few for you, like so, I'll just say etc. These are the terms we get from that recurrence relation. So clearly it's not linear because we don't have the same amount or same difference between those terms. See here we've got a difference of 400, and that's not true of these consecutive terms here. So definitely not linear, that's fine. I think we established that anyway. No common difference. But why is it not geometric? If we want it to be geometric, what we should see is with each pair of terms, so with the 1600 and the 2000, if I have a look at the ratio of that, you'll see I get 0.8. If I then take the next consecutive pair, which is 1260 over 1600, I should get the same value, the same ratio, if this is geometric. Now, if you do that in your calculator, what you'll find is you get 0.7875. Now, since these are not the same, to say they are not equal, this means we don't have a common ratio. Not a common ratio and therefore not geometric. I wanted to clarify that because I have had a lot of students, I guess, question that. So if we're talking about combining geometric and linear growth together, then you would make that assumption that the sequence is geometric or it is linear. But because you've combined them together, the sequence that you get is neither of those things. So just be careful with ones that come up like that. And like I said, like what I've been saying a fair bit actually, best to eliminate all of these ones that you can see are clearly not true before you begin examining the ones that could be true. I'll leave that there so that you can have a go with exercise 9A. And from here, what we're going to do is start looking at these sequences or these recurrence relations, but with a financial aspect to them.